So welcome everyone to the third session. So in this session, we'll be talking about sampling distribution and hypothesis test. Right. So we have started with basic statistical inference. We looked at distribution and correlation in the previous two sessions, and today we'll go a step further. And today is going to be probably the last session for statistical inference, and from next session onwards we'll start diving into data preparation and ML modeling. But today's topic is going to be very important. So we'll look at sampling distribution and hypothesis test. And to do that, we will go to our GitHub location. So if you can go to the GitHub location, I'm going to share that link again. In session 3, in that location, this session 3, I've uploaded some files. So we'll be doing two different notebooks. One is on sampling distribution and hypothesis test. And then we will also do one live coding today. Okay, how to apply all these things that you have learned so far, and especially focusing on today's topic on a new data set. So go ahead and open in Colab, open a link in new tab, and then connect the VM. So I'll just wait for 30 seconds here. So once you're able to connect it, let me know on chat window. Yes, sir, done. Then I'll go ahead and start. So go ahead and open the notebook and say yes on the chat window. Okay. Okay. So we will start discussing about some of the new concepts this week, like variability in mean. Let me take it. So we'll be discussing about variability in mean, sampling distribution, central limit theorem, hypothesis testing, one sample and two sample test. Okay, and these concepts are extremely important, even though they are core statistical concepts. They're very important from the perspective of ML model building. So we'll leverage these ideas or these concepts, right? When you go to model building, for example, we will utilize them in exploratory data analysis or feature selection. So when you select features for the model, in model selection, the model to select which model is better for deployment, and a model monitoring. So these ideas and concepts are going to be leveraged throughout the whole ML life cycle. So it's very important that we understand these key concepts. So let's go ahead and do that. So first we will understand what is variability in mean. To do that, we will load the same data set that we have loaded last time. So let's go ahead and import all the libraries. So we're going to import NumPy, Pandas, Matplotlib, and Seaborn, and then going to load the data set called customers.csv. And if you remember from the last session, this is basically contains a demographics information. So it contains information like customer ID, which is typically not a variable, gender information, income, profession, family size, and age group. And we discussed about also the variable types last time, right? Which variable is of what type in terms of numerical variable, categorical, continuous, discrete, nominal, and ordinal, right? And it contains about 2000 samples, as you can see. Now let's focus on income. Okay. And first look at the distribution of the income, for which we'll do a KDE plot. And as we noticed also last time, typically the income varies from 0 to 200,000 and looks like a bell curve, little bit of distortion there. And the mean income is about 1,10,000, right? And the standard deviation is about 45,000. So we have already understood the concept of mean and standard deviation, and we also understood the confidence intervals, right? Now let's ask this question: does this mean going to remain same if we had sampled another data set, right? Because we have got this 2000 samples here, right? And when we calculate mean, we get about 1,10,000. But of course, this mean is going to change. Even the standard deviation is going to change. Of course, they are not going to change extensively, but they are going to change if we had to sample a different data set, right? Not even different data set. In this particular data set only, if we remove and add few samples, the mean and standard deviation are going to change. Then what exactly the mean value of the population? So how do we actually understand that? So what would be the mean if we have gotten a different sample, right? How the mean would have varied or changed? So all the statistics, typically the parameters like mean and standard deviation, right? They also change based on the samples that we collect. But how much they are going to change, how much there is a variability in those mean and standard deviation, we need to observe that. And that is going to be of significant importance, right, for some of the hypothesis tests. But how do we observe that? Because we have got only one sample, right? And if you want to observe how the mean and standard deviation is going to change for a different sample, we have to collect another sample. But that is going to cost us money and effort, isn't it? We always have to work within the data that we have collected, which is called observed data, right? This is the data we have observed, we have collected, and within this data set, can we also find what is the variability in the mean? Then there is a concept called resample or a bootstrap resampling. So in the process, what we do is we have an original sample here. We have an original sample which is called observed data. And let's say in the original sample, we have S1, S2, S3, S4, and S5, right? And then what you can do is we can bootstrap samples from this original data set and create more sample sets. This is of course called resampling or sampling, right? So there are two techniques out there. One is sampling, right, with replacement, and sampling without replacement. Right? In bootstrap resampling, typically we use sampling with replacement. What does that mean? That means, let's say I create a new sample. Typically the new sample that we create also contains the same number of samples as the original data. But then if you take all the samples and to this new sample, then they'll look alike, right? So then what we do is we sample this from this original data set. And let's say in the first we take S1, right? When we randomly sample it, we got S1. Again, when we randomly take it, we got S2. But when we take a sample, we do not remove the sample from the original data set. It still remains same. So the probability of that sample getting selected again, it's same. It does not change, right? But in case of without replacement, then when you take a sample, that sample we take it out of the original data set, right? So when we sample again, we'll always get a new sample. That typically we use for undersampling. For example, let's say we have a sample of n, a number of samples, and we want to create a smaller sample set, right, with a k number of samples, where k is of course less than n. And then when we take samples to it, and that sample can be removed from here, so that all the samples that we get here are unique and a subset of this original data set. You guys all can mute yourself. Okay. And when you do a sampling with replacement, it's possible that the new sample might contain some of the samples multiple times, which is fine. Okay. So the process of taking repeated samples with replacement from the observed data is called a bootstrap resampling. And then what we can do is we can create this multiple bootstrapped samples from the original data. This is to kind of simulate different sample sets. And here, because we have randomly sampled, so all these bootstrap samples will look very different, which is a kind of represent a different sample sets. And then within each sample set, we'll observe what is the mean value of that. Let's say this is a sample set SS1, sample set SS2. We'll observe how the mean of these bootstrap samples. Okay, so let's do that. To do that, what you can do is you can use a function called sample. So we'll take an income and a sample. We can always specify the number of samples we want to create. So in this case, of course, I'm undersampling. That means I'm creating a sample set which has a lesser number of samples than the original sample set, because in the original data set we have about 2000 samples, right? This is just to demonstrate how the sample works, but typically we would always keep this to the same as your original data set. And there is a parameter called replace, which stands for whether you want to do sampling with replacement or without replacement, right? And if we sample it, a sample one contains 500 samples from the original data set with replacement, and we can calculate the mean value. Of course, this mean value will look little different compared to the original data set samples, isn't it? So this looks like 10731, this is 107405. But of course, we will not take just one sample, bootstrap sample, we will take multiple of it, right? So let's do one thing. We will create 200 bootstrap samples. Typically, we take about 100 to 200 bootstrap samples. Yeah, sample is a random function. And then sample means, we'll create a sample means a list, an empty list, then we'll iterate 200 times. And each time, what we're going to do is we're going to sample randomly 2000 samples from here. Remember, the original also contains 2000 samples, but we are doing with what? Replace and equal to true. And then once we create the sample, we're going to calculate the mean value of it and then add to the sample means, right? So in a way, in this case, what you're doing is we have the original data, and then we're creating multiple bootstrap samples out of it, which contains the same number of samples that original sample, but with replacement, and then we are creating the mean value out of it, right? And then we'll observe how these mean values are varying. So these mean values themselves have a distribution. These mean values themselves have a distribution. All right. So we'll take the list of samples and then we'll create a KDE plot on the sample means. So earlier we created a KDE plot on the data itself, the complete data. So this is called sample distribution. The very unique terms, you must be aware of this terminology, sample distribution, or we call also data distribution, how the data is distributed, right? And if we take multiple samples and calculate mean and look at the mean values, how they're distributed. Okay, so this is the distribution of the mean values, right? And this is called sampling distribution. Okay, just ing if you see here, it's called sampling distribution. So what is sampling distribution? The sampling distribution consider the distribution of sample statistics, for example mean, right? So sampling distribution is the distribution of the mean values taken from multiple samples bootstrapped from the original sample. Okay, and if you look at in the data distribution, the data varies from 0 to 200,000. Okay, but the sampling distribution is saying that the mean value, irrespective of how you sample it from the original data, the mean value typically varies from 1,08,000 to 1,14,000, right? The mean value will always remain same. And in a way, we can also understand that my actual population mean, that means the actual income mean value, the average mean value, the real mean value will be somewhere in between, which is of course not much dispersed, somewhere between 1,08,000 to 14,000, to 6,000 variation, right? And one of the most important concept here is the distribution of this particular mean will always look like a normal distribution. Always look like a normal distribution. What does that mean? That means you may have a variable, or a data whose distribution may look very different. For example, it may look something like this, like exponential distribution, or a very skewed distribution, right? Or different. Remember, we looked at a couple of distributions in the start dist in one of the earlier sessions. But if we take multiple samples and calculate the mean, and we look at the distribution of those means, irrespective of what distribution the original variable follows, whether it follows exponential or skewed distribution or normal distribution, the mean value will always follow a normal distribution. Okay, this will always look like this. Okay, so this is also called a central limit theorem. Okay, I'll come to that. And the standard deviation of this, the standard deviation of the mean, how much it is varying, this is called standard error. This is called what? Standard error. So it's different than standard deviation. Please notice all these terms. Standard deviation. The standard deviation is what? The dispersion in the original data. The standard error is the dispersion in the mean values, right? So how the mean values will change, that's called standard error. And the standard error typically is the standard deviation by the square root of n, the value. So you can actually directly also calculate the standard deviation of the sample and the number of samples, right? Because moment we have a very, very large sample, we will get to know what the actual mean is. The standard error is the standard deviation of its sampling distribution. In this case, the standard deviation distribution of sample means. So sigma divided by square root of n. So if you look at the sample means, I calculate the standard deviation comes out to be 964. And if I look at the formula also, which looks pretty same, okay, closer to that. And then you can also calculate the interval of this, the mean and standard deviation. So let me import the stats. So if you look at the confidence interval of the mean values, it says that the 95% confidence interval is between 1,08,900 to 1,12,000, right? So you can say the 95% confident, the actual population mean is somewhere between 1,08,000 to 1,12,000. These values, a little bit of change, that's fine. Okay. So just to reiterate the concept again quickly, very important to understand. If you have a variable, okay, if you have a variable and you look at the distribution of it, the x value and the frequency of it, right? Let's say it looks something like this. Right? Then of course this particular distribution is called data distribution or a sample distribution, and it has its own mean, which is x bar and sigma x, right? Standard deviation. Okay. But if you bootstrap multiple samples out of it to observe how this mean is changing, right? And you look at the distribution of that, where this is nothing but the x means values, right? And this is the frequency of that. Typically it looks something like this, right? Of course around mean, and this will be the mean of all the means, the mean of all the mean values, and the standard error, right, which will be of course the standard deviation of the original sample is square root of 1, right? This is called standard error. How we are going to use that, leverage that to understand certain inference from the data, will come to that now in the hypothesis test. But this is one of the two important concepts that you must be very aware. Sample distribution, sampling distribution, standard deviation, and the standard error. So there's a question, won't the mean get skewed if you are introducing random values into the sample? We are not introducing random values. We are taking the values from the original sample only. We are not introducing any random values to it, right? So whatever samples we have in the original data. So let me read the question. How is the sampling distribution within the range of the mean? So we are not introducing any random values to it, right? Whatever the original samples we have from S1, S2, S3 to S100, that's 100 samples are there. We are only bootstrapping another sample set which will contain these sample values, okay? But only thing is some of the samples will be multiple times compared to the other samples. In a way, this sample set looks little different than the original sample, right? We'll do sampling with replacement. So when you do sampling multiple samples, these samples will contain the samples from the original data set only, but in a different frequency, right? So it look little different compared to the original data. Okay. So we are not introducing any random values outside those values, and then we'll calculating the mean value of it. And these concepts have a very significant usage in hypothesis test, right? Now, what is a hypothesis test? And hypothesis tests are very important. If you heard about A/B test, right? People do a lot of A/B tests nowadays to introduce new features, right? They do new campaigns to understand the impact of those campaigns, or any intervention organizations do. They want to understand the impact of those interventions. So hypothesis tests are extremely important. So hypothesis test basically analysts use to test a statistical sample. Okay. For example, let me look at some of the examples. Let's say uh, there is a manufacturing unit which introduced a new process, right? A new methodology, and now tries to understand whether new methodology has improved uh, the product quality, right? So they say, okay, is the average number of defective products that is produced by the manufacturing assembly line, has it reduced by introducing this new methodology or not? Okay. So what you do is, when you do the statistical hypothesis test, you first start with a null hypothesis, saying that the average defective products produced is the same before and after the implementation of new manufacturing method. It's a kind of being skeptical. Okay. So you say that no, the new methodology that we introduce does not change anything. And from the data, then you say that average number of defective products produced are different before and after the implementation of the new manufacturing method. Then what you do is, you look at the data and see and observe if the average number of defective products have reduced or not. If reduced, then basically you reject your null hypothesis and accept the alternative hypothesis. But the data that shows that no, the average number of defective products have not reduced, then you retain with the null hypothesis. So this is a mechanism to understand, right? Either because of a some intervention, some change, right? Some treatment, like disease treatment, right? We look at some of the concepts again. Has it really changed something? Like, for example, if you do a treatment with a new drug, right? So they say that, okay, has the drug reduced the overall disease impact? For example, let's say blood pressure, right? So they have the drugs actually have effectively reduced the blood pressure after the treatment or not, right? So another example would be the average sales. For example, let's say you did a campaign or advertisement, right? And your expectation is that the advertisement or campaign has an impact on the sales revenue. So now you observe the data before the advertisement and after the advertisement, and then you look at what and see that whether the advertisement has actually impacted the sales value or not. So typically they have two control groups, right? One is the two control groups, right? Two groups basically. So one with without the intervention, and what with the intervention. For example, you can in this case, you look at all the sales values, right, before the advertisement, and all the sales value after the advertisement, right? And then you compare the two different groups. Same thing for when you introduce a treatment or something. So let's take a simple example here. Let's say a new study claims that children between age of 5 to 10, right, grows at an average of more than 2.5 inches. Okay. So a new study finds that out, right? There's no intervention here. We'll come to the intervention a little later. There are multiple different types of hypothesis tests are there. But existing belief says that typically kids tend to get taller and growing about 2.5 inches only. So in the previous study, let's say some time back, there is an they have reached a conclusion that the kids typically grow at an average of 2.5 inches, right, per year. And then what you do is you look at the new sample data and say, from this data, either you prove that the earlier belief is wrong, or you say that no, I see the same evidence, there is no change in it, so basically you continue with the existing belief. So here the null hypothesis will be what? The average growth in height is 2.5, and the alternative hypothesis basically says that the average is actually wrongly written. The average growth is more than 2.5 inches. So what we do is, let's look at the data. Let's say we did a new study and we received some data, right? And these are samples, some of the samples, and we can see that some of the kids have about how many 100 samples, 100 children's growth we have observed over a period of time in a year, and found that okay, some kids have grown about let's say 3.1 right inches. Some kids have grown one of the kid has grown 3.1, one of the kid has grown 3.6, but one of the kid has grown only 1.6. And you can see some have grown less than 2.5 or more than 2.5. Okay, but then of course we cannot make any decision based on individuals growth. So we look at what? We look at the mean value of it, right? So look at the kids KD plot of that. So some kids have grown lesser than 2.5 and some kids have grown what? More than 2.5. And the average of this particular sample is about what? 2.59. But we cannot conclude anything based on this, though it looks like the kids are growing little more than 2. The average growth is more than 2.5, but we cannot be very certain, because it might be purely by chance, because we are observing this specific 100 kids that's in the sample, right? If you had taken probably different 100 kids and observed, then we might have gotten what? A different mean value. Then what we do is we observe how this mean value are changing using the sampling distribution. Understood? Because you just take one sample and say okay, it's 2.6, so kids are growing more than 2.5. So let's accept this null alternative hypothesis. We cannot conclude like that, because the 2.6 might have come because by chance we are observing this 100 specific kids, right? If you change that 100 samples, the mean value will also change. Then we will do the same thing again here. Of course, there's an API which can directly do it for you, but I'll explain that first, doing it manually. So you can sample 100 samples with a bootstrap sampling with a replacement and observe how the mean values are changing. Okay, and we'll do a KD plot here. So we'll collect the sample means and then we'll do a KD plot and we'll compare with our existing belief that the kids typically grow at what? 2.5, right? So this blue line is your observed growth in height in terms of what? Average growth, right? And this is basically your the existing null hypothesis H0. Now we see that if we had selected another 100 samples, right, and calculated the average of that, it would have remained anywhere between what? 2.3 to 2.9. Then how do we conclude whether it is more than 2.5 or not? Then we look at how much of error, okay, we will make if we accept it is more than 2.5, right? So if we accept that it is more than 2.5, it's more than 2.5, then what? Because we have seen there is a probability that the mean will become 2.5, There's a probability that the mean will become 2.49, 2.48, 2.47, right? So there is a quite a few probability that we would have actually gotten the average value that is either 2.5 or less than 2.5. Okay, and there's also a probability that we would have gotten 2.51, 2.52 and all that, isn't it? So this particular area, in this case, of course, this particular area, it's called the p-value. This is called what? The p-value, which basically means, okay, the probability of getting more extreme values than the one you got from the experiment, right? So how much of mistake you are making, this particular p-value tells that. So if this area is very small, if this area is very small, then we can say that no, we haven't observed this 2.5 or less in the new sample. Most of the times you're observing more than 2.5, right? Then we can accept this particular claim. So alpha is a threshold value or critical value. So how much this area should be, how much this area should be, right? It's called the alpha. It's called threshold value or critical value that we measure the p-value against. So if the p-value is less than that, so it's an extreme observed result that must be in order to reject the null hypothesis, right? Typically we take the value to be about 0.05, right? That means if this particular area is less than 0.05, then we say that, you know, if I had taken multiple samples, only 5% of the times we would have observed the average height to be 2.5 or less. But 95% of the times we would have observed what? The height to be more than 2.5. Then we can say that, yeah, I think we agree. The average growth in height is more than 2.5, not 2.5, right? So if p-value is less than equal to alpha, then we reject the null hypothesis. But when it's greater than alpha, then we fail to reject null hypothesis. But typically statisticians, what they do is the p-value is more than 10%, that area. That means this area is a 10% of the total area. Then they normally say, you know, there is no evidence in the new data to believe in the alternate hypothesis. So in this case, to believe that kids actually grow more than 2.5 inches. If the p-value is somewhere between 0.05 to 0.1, then very weak evidence. Okay, in certain cases we accept, but most of the times again we don't accept them. But the somewhere between 0.01 to 0.05, we say, okay, there is evidence now. We can actually conclude that the alternative hypothesis is correct. Anywhere between 0.001 to 0.1, strong evidence, and less than 0.001, very strong evidence. Okay, typically people use it, but this is again a thumb rule. In certain domains, people say it has to be less than this 0.01. Certain domain people use 0.1, but most people accept this significance value of 0.05. Okay. So based on what test you are doing, okay, you check the p-value. So in this case, we are saying that what we are observing in this particular scenario, what we are observing is more than the existing belief, the mean value, so more than 2.5, right? But in certain cases also, in scenarios where we also saying that what was the average value that we have accepted so far, it is less than that, right? Then we look at the right tail of it. Okay, this is typically called left tail. Okay, this is called a right tail. There are also two tail test also there, but I will just leave that for you to explore. Okay, so if this area is less than 0.05, then we reject the null hypothesis. But if it's more than that, we don't reject it. Same thing, if it is less than 0.5 on the right side, we reject, otherwise we don't reject it. Okay, So here in this case, because we are observing this 2.5, right, and this area is probably more than 0.05, we're going to measure that now. We'll probably not reject and we'll still retain the null hypothesis, saying that we haven't observed anything significant evidence to conclude that kids grow more than 2.5 inches. Now, alternatively, let's say we have received the following results instead of the earlier one, just to compare it. Let's say instead of that data, we would have received this, let's say, just to explain, right? And this of course shows that the average is 2.72, but this could be again by chance. But when you look at that sampling distribution, now we see that if we take multiple samples of this, right, we see that most of times we are observing the average height to be somewhere between 2.55 to 2.99, and most of times is more than 2.5. So this is the case where we can conclude saying that more than 2.5 inches. In this case, we can reject the null hypothesis and accept the alternative hypothesis. Okay. And this is called one sample t-test. Okay. T-test is a type of inferential statistics used to study if there's a statistical difference between two groups or not. Right. So SciPy has a test sample, t-test API. So there are three different tests are there actually. Again, I'll come back towards the end to explain what are the three different ones. So one is, in this case, we are doing a one sample test because we are comparing with a population mean. So existing belief is kids grow about 2.5 inches, and we'll give this particular sample saying that, do you see enough evidence in this sample which says that it is not 2.5, it's different than 2.5, right? So you're going to test that, and if you do that, it basically says the p-value is about 0.033. Okay, I'll come back to some of these concepts later, but just focus on p-value now. It says the probability that we are finding the average height to be 2.5 or less than 2.5 probably is about 0.33. So in this case, what we'll do is we will conclude saying that the null hypothesis is retained. Okay, we will not conclude saying that the kids actually grow more than 2.5. Right. But if you look at the other one, so in this case, it's about the area is about 0.33. But in this case, if you look at it in the other data set, the p-value is about 0.002. So this particular value, the probability is about 0.0002. So the p-value is extremely small. So you can actually reject the null hypothesis. But of course, in the real world, you won't get two different samples. You'll always get one sample, right? So within the sample, we can actually conclude whether to accept or reject the null hypothesis. Okay. So this is called one sample t-test. So first, let me look at the different types of t-test, and then we'll explain one more example. So there's a link there. You can actually look at this particular example here. So there are three different types of hypothesis test we do, right? One is called one sample t-test, okay, and one is called independent samples t-test, right, and one is called a paired sample t-test, right? And you must know when to apply what. One sample t-test is when you just have one samples, okay, taken from the original population, and you are comparing it with the population mean, the existing belief, saying that so far the belief is this, the mean value or average value is this. Now I have collected one sample and going to check whether it is different than what we have believed so far. So investigate whether there is a difference between the group and the standard value, right, which belongs to a population. But sometimes we may have the two different samples, right? Of course, one of this we are going to do it now, but they're independent. For example, let's say you are making a changes to a website, right? Let's say your UX designer says that if I design the page, typically it's a wonderful case for A/B tests. The UX designer says that if I design the page differently, then the interaction with the user will be much more impactful, which will ultimately generate more interest or more revenue. Okay, then what you do is to verify that, right, before you switch over to the new design, what you can do is you can have the old page, right, and the new page, both are going to be live, right, and you randomly show the pages to the users. So a group of users, right, a group of users would be shown the old page, and the group of users would be shown the new page. And then what you do is you can observe how the old page is this particular user is interacting with the old page, and this particular group of users interacting with the new page. So either in terms of amount of time spent, like a session duration, or in fact you can also look at how much conversion has happened, right, how much sales revenue has been generated to two different pages. Then we compare it. So this is one sample set and this is one sample set, and you compare, saying that are they different, or this is better than this, greater than or less than this, right? Those comparisons you can do. That is called independent samples t-test. Investigate whether there is a difference between two groups, okay, between subjects. So the users are different, the groups are different here. But there is also something called paired sample t-test, okay, where the same group of users will go through an intervention. Okay. This is typically used for treatments. Okay, the same group of users will observe, let's say for a duration of time, will observe, let's say, their blood pressure, right, and then they will go through a treatment. Okay, they will go through a treatment, and then again will observe their blood pressure, and say this treatment has any effect after the treatment, right, on this particular set of users. So here the sample is still same. Investigate there is a difference within a group between 2 points in time within subjects, right? So here the samples don't come from two different sets of subjects or users. Okay, same set of users, before and after effect. This is very important, right? So that's called paired sample t-test. So these are three important t-tests that you must be aware, because we might use them in the model monitoring and all that, and designing our A/B test to understand the effectiveness of the models in the real world. Okay, of course these are a core statistical concept. They are applied a lot of other domains and different kinds of cases, but from the ML perspective, this is very important to understand the for model deployment and model monitoring perspective. Okay, so let me go back to the notebook again. So I have a simple example here to do a two sample test. This is actually two sample, not paired test. So let's say company XYZ, which offers services, has upgraded their catalog web page, very similar to the one that I'm explaining now, wants to verify which of the two web pages is better at selling, if the old page is better or the new page is better, right? So one thing you can do is we can actually observe sales revenue, right? So typically sales cycle is lengthy and takes about 2 to 3 months to complete the sales. So it'll take a long time to gather enough sales data to verify which page is superior. Okay. So instead, we can also use a proxy variable. Right? Of course, we can show the web pages. Typically, these experiments are not run for a very long time. This typically runs for like few weeks. And if you your data that is required to verify which is better, the cycle is very long. Let's say sales cycle is 3 to 4 months. Then you can't run this experiment for 3 to 4 months, right? So instead, what you do is you can use a proxy variable. Let's say there is a understanding or establishment, right? Saying that it may have been established from earlier data that the session duration is highly correlated with actual sales. The time people spend, right, on the web page or on the site is highly correlated with the actual sales, positively correlated. Let's say you have already this understanding, the assumption from the before. So instead of looking at actual sales, you can also observe session duration. Okay, so not necessarily you have to use a proxy variable. Sometimes you can directly use the actual variable itself, but sometimes you can also use a proxy variable. Okay, so the amount of time user spends on the page is called the session duration or the session length. So when you do the test, first you have to understand which variable you want to observe, which variable you want to measure, right, to see the actual difference. The actual what? Difference. So in this case, let's say there's a data set here, sessions data, and there's an old page data and the new page data. So about 1,000 users which has visited the old page and how much amount of time in terms of seconds they are spending, right, on the old page and the new page. And then we can observe them. So you can see that the distribution, this is a data distribution. Remember, this is a data distribution of both the old page and the new page. This is the distribution of session duration for the old page, and this is the distribution of the new page. And you can see it's a lot of overlap there. Of course, the new page has definitely little more probability of higher session duration, more than 350 and all that. But there's a lot of overlap. The people who are spending even lesser than the old page, and there's a lot of common, right, between old page and new page. But are they significantly different? Then what we do is we will create multiple samples out of it and multiple samples out of it, and then observe the distribution of their averages and check if the average duration, what you are checking is the average session duration, right, the average session duration for the old page, okay, and average session duration of the what, new page. Okay, so are they look very different? We simply cannot calculate average and compare, because like I told you, they could be by chance, right? So multiple samples will take. So here for the old page mean and the new page mean, right, I'll take multiple samples here, and yeah, and then we'll compare it, right? So the original number of samples are how many? 1,000. So I'll bootstrap 200 times 1,000 samples and calculate their mean and look at that, and same thing for this, and do a KD plot on top of that, right? So this is what we have done so far. And I'll just quickly show it here, right? Yeah. So if you look at the distribution of the average values for the old page and the new page, they look very different. What it says that the average session duration for the old page is somewhere between 300 seconds to 305 seconds, whereas the average session duration for the new page is somewhere between 300, let's say 12 to 325, isn't it? And there's no overlap here. It's definitely better. Of course, how much better we can compare, but definitely better, right? And then we can do a t-test now. So in this case, we are doing t-test independent test. Remember, this is not one sample test, In the earlier one, what did we did a one sample test because we're comparing with what? An established mean value, the population mean, we can assume that. And but here we are comparing two different samples, right? The samples of the old page and the samples of what? New page. And then if you do a test, it says the p-value is very, very small. That means the likelihood that the average session duration of the new page is same as the average duration of the old page, the probability is extremely low. So you can conclude that is basically different. And here the negative means there's also a value of negative or positive in terms of statistics. Negative means what? Typically the average of this first sample, the average value of the first sample and the average of the second sample, right? Negative means what? This average lies to the left of this. That means this is smaller than this, right? So average session for the old page is less than the average duration of the new page, right? And if you it's a positive means the other way around. We can actually quickly check that. So if I give this one, let's say I give this one as a first parameter. Let me do this one. If I just copy paste this one, so you also have to very carefully give the first and second parameter. So let's say you give the new page and the old page, the other way around, right? So here t star is coming to be positive. That means saying that the average of this is more than the average of this. So then we can actually know which is better or not better, right? So that we have to very carefully give the parameters, which is the first and the second parameter. And hence, because this p-value is almost less than 0.05, right? Then we actually our null hypothesis here, I have not written here, but the null hypothesis is rejected, saying that both the session durations, average session duration for the old and new are same. That is rejected, and we accept that the average duration of the new page is better than the old page. And sometimes see, this is of course just better, right? But sometimes what you do is you can also run analysis saying that how much better, right? Maybe you look at an example in later sessions, but typically A/B test, what you do is, let's say we run a campaign. In the A/B test, we run a campaign and say, has the campaign increased the effectiveness by 10%, right? Or has it increased by at least 30 seconds? So in this case, we will say, is the average duration, session duration, is increased by 30 seconds or not? Okay, not only better, but it should be at least whatever the average of the old page plus 30 seconds, right? So of course, then in that case, you can actually add the 30 value here and compare the results. We'll look at probably a couple of examples of A/B tests later sessions. Then we'll come to some of those problem formulations. But this is the the foundation of hypothesis test. Let me quickly go through some of the concepts again. So when you take a sample and calculate the mean value, okay, so that mean value is not constant, right? If you take a different sample, the mean value would change. Now we want to understand how that mean would change. What is the variability in that mean? But how to do that? We don't have multiple samples, so we'll bootstrap multiple samples from the existing sample. So we'll use something called bootstrap sampling with replacement. So we'll create multiple samples which look different, but they contain the samples from the original data set. And then we'll calculate the mean value of all of them, right? Mean value from each of these samples and look at the distribution of that. And this is called sampling distribution, but this is called what? Sample distribution or data distribution. And this distribution will always be a normal distribution. Okay, that is empirically found, and it's always normal distribution. Okay? And the dispersion or the standard deviation of this sampling distribution is called the standard error, and which is nothing but the standard deviation divided by square root of n, number of samples that we have. So the larger the samples you have, okay, typically this distribution will look what? Even smaller and smaller and smaller. Like the distribution will look very small. Okay, and if you have infinite number of samples, then we will get the actual mean value, right? You understand that? Because if you have infinite number of samples and we calculate the mean value, that's the actual mean value, isn't it? So we don't have to, because we have almost everything, all the data. So whatever the mean value will be the actual mean value. So the moment n becomes infinite, right? So there is no dispersion in the and then based on these concepts, we are doing multiple hypothesis tests. All hypothesis tests have the problem formulation is a null hypothesis and alternate hypothesis, right? Null hypothesis basically assumes that there is no relationship or that there is no change. Okay, it's a status quo, saying that no, we don't see any evidence. Okay, so we'll believe what we have been believing so far, right? Alternate hypothesis basically saying that we have a new sample which says otherwise what we have believed so far. So let's test it, whether we will continue to believe in what we are believing, that means the null hypothesis is correct, or we'll change our belief to the alternate hypothesis now, right? So a couple of examples here, and there are three kinds of tests like I told you. One is one sample, two sample, and pair test, and then we look at that the evidence of the evidence in the new sample, right? So in this case, what is the probability that we accept the alternate hypothesis, right, but we still see the evidence of the null hypothesis here? If that probability is very low, then what we have observing here is we have never observed in the null hypothesis, or we have observed only very few times, like 5% of the times, and what we are observing is a 95% different. Then we accept the alternate hypothesis, right? So I've given, typically there's something called p-value, which is nothing but this area that we calculate, right? This area that we calculate, and alpha is basically is the threshold value. This is like we compare with this alpha, all right? So the alpha is less than 0.05, then normally we reject the null hypothesis. If it's more than alpha, we fail to reject. Okay, that means we retain the null hypothesis, we call it. Okay, so we looked at an example of one sample test and two sample tests. Okay. What I'll do now is I will look at one more example, a little different example, right, called chi-square distribution. So let's look at that. How much time? So chi-square distribution. So chi-square distribution is a hypothesis test to verify whether the observed frequency in the data is same as expected frequency. Okay, let's take a simple example, right? When you toss a coin, right? When you toss a coin, the probability of getting head is how much? 0.5, isn't it? And the probability of getting a tail is how much? 0.5. Okay, if it's a fair coin, and of course let's assume that it's a fair coin. That means if I toss 10 times, if I toss the coin 10 times. So I'm expecting what? 5 heads and what? 5 tails. This is called expected frequency, right? Based on our uh, assumption that this is a fair coin, the probability of getting head is 0.5 and the probability of getting tail is 0.5. So I'm expecting if I'm going to toss 10 times, I'm going to get 5 head and 5 tails. But let's say, of course, in the real world, you will not get, right? Let's say you got 6 heads and 4 tails. Okay. So that means, are we going to conclude saying that this is not a fair coin based on this observation and say no, the probability of getting a head is 0.6 and the probability of getting a tail is 0.4? Isn't it? So we can test that using chi-square distribution. So now just to understand, right, how this works. Of course, it has its own distribution, binomial distribution. For example, if you toss two times a coin, right, you might get 2 heads. All right, and then of course you will say no, this coin always shows head. The probability of getting head is 1. Probability of getting tail is 0. Right, because I got 2 heads. But if you increase the number of samples to 10, there's a 10. Now what happens is you will get some more tails now. So the probability of getting tail, which was here 0, will not be 0 anymore, right? So what happens is when you do it infinite number of times, infinite number of samples, then you can observe that typically we get about 50% head and 50% tail, right? But we cannot have an infinite sample. So what we'll do is we'll observe a large sample and see if that observed frequency that we are seeing is same as expected frequency, just because of chance we are getting different numbers, or you're looking at very different frequency distribution, right? So probability of getting head tail, of course, we'll look at this. So now let's take a simple example saying that your retail chain, right, and you want to run a campaign or do customer profiling or whatever. Your existing belief basically says that the proportion of customers from all age groups are same. People who are coming to my retail store, okay, your existing belief that typically customers from all the age groups that come to the retail stores are same. There's no difference in their frequencies, right? That means if 90 people come to retail store, 30 would be in this case I am showing the actual age group 1, right? 30 will be from the age group 2 and 30 will be from the age group 3. But to verify that, what we'll do is we'll randomly look at 90 people. So in this case, let's look at sample data. And you see that when we collected data about, I think we have collected about 99 people here, 99 samples. So because randomly looked at and sampled the data, and then we saw that about 28 people who are young, maybe less than 25-year-old. About 40 people out of that were, adults, which are like 25 to let's say 45 or 50, and people who are more than 50, about 31. But does this evidence, now we will conclude saying that, the more adult people coming than the young people and the old people, or we will still say that no, they're typically all same. Okay, so if you look at the bar plot also, the visitors DF, age group and count, you can see that more adult people are coming than the number of old people and young people, right? Then we'll look at something called chi-square distribution, right? So chi-square distribution, typically we do something called a goodness of fit test. right? So what it says chi-square basically is, um, it verifies, done to decide if one variable is likely to come from a given distribution, or to verify the observed frequency in the data is the same as expected frequency. Okay. So let's say this is the observed frequency, which is nothing but 28, 40, and 31, and the expected frequency. Typically, in the real distribution, I would have seen 33 young, 33 adult, and 33 what? Old people, right? That's the expected frequency, right? And the chi-square distribution is calculated like this: observed minus expected square divided by expected, right? So in this case, it would be like, what's the number here? 28. You can basically say 28. 28 minus 33 square divided by 33 plus 40 minus 33 square divided by expected 33, and 31 minus 33 square divided by 33. Okay, so this is we'll calculate this value, and then we'll see in the chi-square distribution. Typically this will follow a chi-square distribution. What is the probability of looking at this number, and that we can actually calculate using this chi-square here. And what it basically saying that the probability of observing this particular frequency, even when the real frequency is 33 or 33, the p value is what? 0.30. That means there is a possibility that even if this frequency is the actual frequency and we're observing this, we can actually observe this. There's 30% chance that we might actually observe this. Okay. So here, because the p value again is more than 0.05, right, we will not reject the null hypothesis, basically saying that people from all age groups, okay, and the number of people from all age groups that come to the store are still same, they are not different. Okay, that's basically this is primarily for categorical features, right, because these are categorical features, and these tests are typically for the numerical features that we do, continuous features. Okay. So the two most important hypothesis you should always remember: one is your t-test, right, is a one sample test, two sample test, or pair test. I haven't done a pair test here, but we'll do it in some of the future sessions. And the chi-square test. This is primarily for your numerical variables. Okay, because you are comparing the mean value. Remember, we're comparing the what? The mean value. Is it smaller, greater, or the same before and after? But in chi-square, we're looking at the frequency of the categorical features. Okay, we are expecting some frequency and we are observing are the same or different. Okay, so these two are going to be very important from the perspective of data analysis and models monitoring and all. So that brings us to the end of this particular notebook. Okay. So what I'm going to do is I'm going to give you a 10 minutes break here, right? So we'll come back and join at 10:30, and we'll quickly look at one more example, and that example I will extend as an assignment for you for this week. I'll show you some basic ones, and then we'll conclude today's session. Sound fine? So now we will look at the application of all this to a real world data, and this will be like live coding. Okay, so what I'll do is I will take you certain steps and leave out certain steps as an assignment for you to do it this week. Okay. Uh, so I'm going to do this on the local system. So my assumption is, of course, you would have already installed it on the local system. So you can go to any folder, or if you've already downloaded, you can go to session 3 also. Anyway, we're going to read the data directly from the repository, so it should not be a problem. So either you can follow me now, or you can observe and do it again when you watch the video on your system. Right? So you're going to create a new notebook now, new Python 3. Can you just confirm if you're able to see properly on the chat window? Yes. Are you able to hear me and see the screen properly? So you're going to name it like a CHD analysis. I'll tell you what CHD stands for. And then you can go to the Chrome, Google Chrome, and search for something called Stanford. Let's say, why it's not working? Stanford SA Heart Data. I'm going to also paste this the link. So there's a Stanford data set called SA Heart, and let me paste that on the chat window. This link. So this is a data set from the Stanford site. They have collected this data, and this is a retrospective sample of males in a heart disease high risk region of South Africa. There are roughly two controls for the cases of CHD. CHD stands for coronary heart disease, right? So many of the CHD positives men have undergone blood pressure reduction treatment, other programs to reduce their risk factors and all that. So in this case, you can see there are multiple parameters that have been collected from the people. So systolic BP, which is the high blood pressure, tobacco consumption, LDL, which is a bad cholesterol, adiposity and obesity are kind of measuring the fat. Family history, if the person has a family history of heart disease or not, alcohol consumption, age of the person, and CST, whether the person has a CST or do not have a CST, right? And there's a link there here. You can copy the link and then go back to the notebook. You can say import pandas SPD, right? And then you can read the data. Let's say we're going to give it a CSTDF equal to pd dot read CSV, right? And you can directly give the URL. It's going to read the data from the internet. You can also give current location. You can directly give an HTTP URL also. Of course, it's going to take few seconds to read the data. Now it's read, I think. So CSTDF, if you look at the head, right, you can see so each row is about a person and whether the person is suffering from CSD. 1 means has CSD, and 0 means what? No CSD. Right. And then of course there are many other parameters. This is actually a row number which you can ignore. Blood pressure, tobacco, LDL, and so on and so forth, like we observe. You can also see how many uh, observations are there, info. So about 462 samples are there, and out of that, I think most are there filled. There's no missing values here. Okay. About 11 columns. Out of that, of course, one is the row name, which we can ignore. So about 10 columns are there. Now, how many people in this sample have CST and do not have CST? To know that, what we can do? We can do CST df dot CSD and value counts. Remember, we can do value counts. So out of that, 302 do not have CST and 160 have CST, right? And which you can also kind of uh, depict in a count plot. So you can say import matplotlib dot pyplot splt, import cbonage sn, right, and say sn dot count plot. Remember, we did this data equal to CST df and x equal to CST. So you can see the number of people in CST and no CST. And if you want to know, let's say take one or two examples. Let's say take an example of tobacco consumption. All right. So if you want to understand, okay, is the tobacco consumption distribution, people who are suffering from CST, the tobacco consumption, how much they smoke, is it very different than the people who are not suffering from it, right? So you can look at what? We can look at the distribution of it, right? So if remember, you can do a KD plot, data equal to again CST df and x equal to tobacco, right? Tobacco. Yeah. But this is the tobacco consumption of all the people, right? This is a tobacco consumption of what? All the people in the sample, whether they are suffering or not suffering. You can see some people have a lesser consumption. This is, of course, negative means it's just a smooth distribution. That's all. You can also do a histogram if you want. And some people are very high amount of consumption, right? Now what I'll do is we can divide these two groups, one into CST group and one to no CST group, right? So you can collect all the let's say CST, I'm just giving a name, and then say CST df where CST equal to 1. So this group will contain this sample group will contain the observations of those people who are suffering from CST. Similarly, I can also say, no CST. So this particular will contain the samples from all those people who are not having CST. Okay. Now if I compare, right? Now if I compare the distribution plot, so I can say sn dot kd plot, right? Data equal to CST, right? X equal to tobacco. Similarly, no CST. I can overlap both the CSTs. I can see there's a difference, right? So you can see some difference like we did before. Remember the session duration for two different pages. Now of course we cannot understand which belongs to what, so we'll actually add a label to it. So we'll say label equal to CST and this will say label equal to no CST, and then you can add a legend also, right? Yeah. So the blue line belongs to people who are suffering from CST, and the orange line people are suffering from what? No CST. right? So you can see there is of course some evidence that the people who are suffering from CST a little higher consumption of tobacco, but it is so if you now set a look at average of both of them, right? So yes, CSD, you can say tobacco, right? The mean value of it is about this, and the no CSD would be of course lesser than that, but there's a lot of overlap there, right? But it's statistically significant. We can do a hypothesis test here, right? We will basically say my H0 is saying that the tobacco consumption, right, of people who are suffering from CSD, right, is same as tobacco right, consumption of people who are not suffering from CSD. Let's say that's my H0, okay, and this is my H1. Basically, I'm saying that it's not same, right? You can actually write it like a formula, of course. So we'll do a hypothesis test now. Does it look very different or not? Then what kind of test we will use it here? Because there are two different samples are here. I can use the two sample test. So you can say from SciPy dot stats, right? Or from SciPy import stats, and the stats dot t-test. You can see the moment you tab, it says whether you want to do a one sample test, independent test, or relative test. So if you look at the documentation of SciPy t-test, t-test in t-test sample, right? T-test sample, you can actually do it for one sample test, which is you can give a sample and compare with the population mean, like we did for 2.5 inches. Give me a second. And we can also do independent test, where we're giving two samples here, sample A and sample B, and compare it. And we can also do relative test, which is nothing but your pair test, right? Basically the related samples. So three different tests are there. So in this case we will do a independent test. So we'll take CSD and the tobacco consumption, no CSD tobacco consumption, right? And you can see the p-value here. The p-value is extremely small here, less than 0.05. Then we know that the average tobacco consumption of those people who are suffering from CSD is very different than what the tobacco consumption of people who are not suffering from CSD. And the positive means, like I told you, this particular the average tobacco consumption here, right, for people who are suffering from CSD is greater, right, than average value of people who are not suffering from CSD. So this is because positive value, this is great, the average is greater than this particular value. So you can, here you can see that the tobacco consumptions are very, very different. Okay. So this is one. So what you can do, you can do it for rest all variables. So I'll give you, of course, as an assignment, you can do it the same thing for rest all variables. You can do the distribution plot of each one and the groups and the statistical test. But I'll do one for categorical features. Now let's look at categorical feature here, family history, right? Family history. Now, people who are suffering, people who have a family history, let's say fam hist equal to CSD dot fam hist, right? Present, right? Will be equal double equal. So this will contain, the fam hist will contain, there's about 192 people there out of this 400 samples, the people who are having family history of CSD. Now, out of those, how many people are suffering from CSD? Now you can say CSD dot value counts, right? So out of the people who are suffering from CSD, there's 96 and 96. Okay, so you can see that the equal probability here, isn't it? So now if you assume that, let's say the assumption that people who are suffering from family history typically will have a CSD, and people who are not suffering from family history, isn't it, will have a CSD. So then you can do a chi-square test. Okay, so I will leave it here for you to explore this. You can also do it for the people who are absent, right? No family history. And if you look at no family history, CSD dot value counts, right? In fact, if you look at people who do not have family history, there are how many people are there? There are about 270. Out of that, 206 do not have a CSD, right? And 64 have it, right? So you can actually do a chi-square test to find out the chi-square whether the expected frequency is same as the observed frequency or not. We can do that. So this is going to be an interesting data set. We will explore this data set further for model building also later, and do a little bit of EDA as well. But it's a good one to look at each variable and look at the hypothesis test and understand the variables and all that, right? So I will close the session here today, and you can complete all the steps and upload this as an assignment. Couple of things. One is, give me a second. When you are doing the assignments, you also do the documentation, right? Because as a data scientist, you also have to inculcate this habit. You to develop this habit that along with the code, how to organize the code, how to do write comments, what you're doing, and what's the inference and all. That's very important, because don't do the assignment just for the knowing, but also from the perspective of showcasing. So tomorrow, if you can want to show the all the assignments on the GitHub project, and somebody wants to look at that, so if you properly define the problem, properly define the steps and all that, it will be much more impactful than just the code. So you're anyway doing the hard work of doing the assignment with just additional half an hour of effort to kind of structure it beautifully, write the comments and all that. So that will actually help you later to showcase your work, in case right, you're looking for an opportunity and all that. Okay. So with that, I'm going to stop the today's class.